voice.
Yeah, so before we go into all the tool changing stuff, just wanted to talk a little bit about what we've been doing in the general hot end and extrusion systems and all of that. So yeah, V6 been out for very basically every single part of it has been completely redesigned and it's built from the ground up. It's like the, what do they call it, ship of Perseus, where you change every part, is it still the same one? But yeah, I think the biggest enhancements are some of the things we've done very recently in regards to upgrading all of our machining. One of the most critical components, the hot end, the heat breaks and the nozzles. So those are now have drastically improved surface finish. So the inside of the heat break tube surface is much finer. Morning, come on in. We don't have a microphone, so PA, so sit close. Yeah, those internal surface finishes are much nicer, much more consistent. And the external surface finish of the nozzle is vastly improved, which is important for making your top solid layers smooth and things like that. So generally, extrusion reliability and consistency just keeps like creeping up, and also reducing the pressures required to extrude as well, so back pressure and the amount of force that is required to restart extrusion after a retraction. So there's a small amount of stiction in the hot end that you have to make like static friction, so that you have to input a little bit of force and you won't get any movement until you reach a certain force threshold, at which point you kind of get out of the stick into the slip regime and the material begins to slide down into the bore. So all of those forces much reduced. The heaters, I've just been out to China actually to see the heater manufacturers. They are just so much different from the cartridge heaters we had when we were first starting out. They're much more consistent from part to part in terms of their resistance, which isn't a huge deal for you guys in here, but for people, hundreds of hot ends per week, or even thousands of hot ends per week, having the heater values be consistent from printer to printer that they're building is really important to them. Makes PID tuning a lot faster, easier, and all of those things. They're also much more reliable. The MTBF, mean time between failures, is much lower, so they have kind of in the hundreds of thousands. Oh, hello.
You only need a couple of questions.
I know. I saw my ridiculous hair out. I can't get rid of it now. It's like part of the E3D branding, to the point where the marketing team put it on the boxes. Yeah. Yeah, scaling up production to meet demand. So we're just installing a lot more machinery. It's newer, it's better, it's great. We've dealt with the whole bearing issues. Has anyone had a problem with a Titan bearing degrading? Because no one in this room to their pitchforks. We had some issues with the bearings that goes all the way back to some lubricant actually chemically attacking the lids of the Titan extruder. So the Titan extruder has a bearing that's pressed into a plastic part, and we were getting what's called environmental stress cracking, which is where you have a stressed part and you introduce a chemical, and you need this like particular interaction of certain lubricants, certain amount of force, heat, and so on, and it all led to the cracking. So we changed the lubricant, but then the manufacturer didn't put the lubricant in properly, so the bearings were failing. Yeah, it was a shit show basically. We went around in circles on that, but that's all sorted now. We've changed the material that the plastic part's made of, changed the lubricant, and manufactured that bearing, and everything is fixed. Cool. Things that we've been planning too much time here, but we've been working on systems to enable printer manufacturers and people here to want they see high-end materials, so your kind of peak Sultans and the like. Those sorts of things require hot ends and beds that can go to very high temperatures and maintain those. So we're about to release some beds that can go to 200-300 degrees. So already have in stock and have done for quite some time now. Hot end systems that can go up to beyond 400 degrees. So you have to replace a bunch of materials. So like aluminium, for example, begins to fail around like 350 or so. And when you like creep up towards 400, it's kind of like mushy, sort of putty-like. So a bunch of different alloys. Water cooling so that you can have hot ends that work in heated chambers, because if you have a fan, you can't fan cool heatsink with hot air for obvious reasons. New support material, which is really cool, is this stuff called scaffold snap, which is a breakaway support material, and it's like super weak and brittle. And then afterwards you break it off and it separates clean from the build material. And we've been doing tool changing, times faster melt flow volume per second, if you like. Then there's Rocky, which is kind of like Chimera, where you have one milled square heatsink with two nozzles coming out of it, but instead of having the two nozzles side by side, they're like this, and then we put a bearing in the middle of the heatsink, and we can use a servo or similar, or even the motion of the carriage to flick the hot end from side to side, and a precise way, there's a precise mechanism in the detent, and also adjustable mechanism in the detent that allows the hot end to return to precisely the same position every time and maintain that position. So that's quite fun because you can retrofit it. It's really nice for like an i3 or similar, those kind of where you have the two X carriage bars like that, and you want to retrofit it and upgrade it to dual extrusion without too much hassle. It fits on the kind of space that takes the one hot end fits onto. You get two in there and the rocking mechanism. So yeah, it works well. It's nice. Aero V2 Mini is what we're working on mostly at the moment, which is Titan Aero, which is an integrated, filament drive extruder system with the hot end all in one compact package. So that is, we should realize in the order of a 30 to 40% mass and volume reduction, whilst also reducing the price. So it should, the cost should come right down compared to the current Aero, which is about £90, 110 euros in that order. We should be getting hopefully close to 2/3 to a half of that. So yeah, we're kind of moving to higher volume production processes. But more about that when it comes out. Pardon me. We have a coating for nozzles that stops plastic sticking to it and building up. It's not 100, it's not like super hydrophobic, when you see the sneakers and you put mud on it, it just falls away. It's not quite like that, but it does significantly reduce the amount of plastic that just builds up on things, so that's good. And that should be going on our hardened steel nozzles to replace the current black oxide surface finish that's on there at the moment. That's finished, don't know where to pick up. Smaller nozzles, 0.1s coming out soon. With a high temperature sensor that isn't a PT100 or a thermocouple, and you can directly input. So it doesn't require any external amplifiers or madness like that. It's basically a high temperature thermostat. So a thermostat that you can plug in and it will run to 500 degrees or so. So that will be good. It makes printing these kind of old heavy aerospace PEEK type materials just a bit easier with less hardware complication for that stuff. We've got those, the very high temperature heated beds. Project code name at the moment is Mordor, that the engineers chose. Cool. What most of you probably came here to see is the motion system. So that's the entire anything shut out. This in the way that you buy it, in the way that we do tool changing. So how it can be done in an easy, simple format and give them a platform that is good for the kind of 3D printer company based designs on, but also for the pickup and buy. So that's why we don't include any tools. And on the electronic side, there's only really one board on the market that currently really works with tool changing with 4 heads, which is Duet. Get into that in a moment. But we want to encourage more firmware developers and the companies that make the boards, like Ultimachine, etc., that make the 3D printer driver boards, to create boards that have more I/O on them, so that we can drive all of these crazy heads. So it's like this to try and encourage the general kind of ecosystem to build up in the community and in companies, so that it can, this whole tool changing thing can happen, not just as a E3D only and like a little closed bubble, but have it as a wider kind of ecosystem supported by a multitude of companies. It's not cheap, because we're using a lot of expensive components and fairly pricey manufacturing methods. So we're machining the top plate and we're using a bunch of high-end parts I'll get into more along the way. But it's because it's a reference platform with very few compromises. We've still designed it for manufacturing and so on, but yeah, it's pretty uncompromising in terms of its build and the components that we've used. Cheap, but it is very, very, very good. So I'm going to spend a little bit of time on the motion system. The motion system on this printer is kind of like an exercise in textbook motion system design without any of those normal horrible constraints like price or will it be light enough to ship. He's like, all of that, throw that in the bin. Let's design a printer from scratch that has an incredible motion system. So the whole motion system is mounted to the single machined aluminium toolkit at the top. So both XY motors, you've probably all seen it out there, but it's a U-shaped milled piece of aluminium, and all 3 axes mount to that effectively. So the 2 XY motors bolt directly onto that. The entire motion system is on standoffs, or the belt paths are all defined by standoffs. And also the Z-axis motor is also the back end of the Z-axis motor bolts up hard against that main motion plate, as we call it. So it's extremely stiff and very, very repeatable. And the way in which everything is fixed improves the perpendicularity of the Z-axis as well. So obviously with a machined object, you're going to get very good perpendicularity in X, Y, but also having the Z motor bolted back up against the plate as well. The other point I'd just like to make is that although the tool plate is extremely flat anyway, kind of out of the factory, really the flatness is defined by the fact that all 5 of those extrusions, as long as you cut them to precisely the same length, when you bolt them down with a very high amount of assertiveness, because you've got this big bolt force multiplier, it's going to bring that plate into a very stable, flat, planar position. And then we kind of build off of, why is that not? Okay, we're going to this. So then we kind of build off of there. So we see that we've got the motors, and they are on machine standoffs that just space them away to get the kind of pulley portion aligned with the belt path. But again, as machinists, on a lathe, as long as you produce these 4 parts with the same length, then it's going to be, the pulley is going to be extremely flat and straight and in line. It's also extremely stiff, so there's very little deflection in the system, extremely little deflection in the whole system. And so there are 2 planar belts. By planar, what I mean is that there aren't any crossing XY belts at the back or any out-of-plane belts. And so the other motor that drives the other belt is just on slightly longer standoffs that stood away some more.
What material are they made of? Because they're brown and not black.
Oh, the belts.
Yeah.
Yeah, so the belts, the rubber material is EPDM rubber, i.e. neoprene, which is a classic black material. And then on the brown side, on the tooth side, it's got a non-woven nylon fabric, basically, that the EPDM has been molded over. Two reasons for that. One is it stops it reduces friction. It means that the belts kind of settle into position in the tooth. So you've got the socket, if you like, that the tooth of the belt goes into. And EPDM is quite sticky, so it can kind of stick on the edges. You get some slight positioning error based on the amount of force that was applied as the tooth settles and the direction in which the tooth entered the belt. So the nylon provides kind of a self-lubricious facing material. It reduces wear on the belt as well. It means the belts have a much higher wear life because EPDM rubber does not have a high wear life, whereas nylon does, especially against smooth, flat surfaces with not very high PV values. So you have very little wear. The reason why we chose them as well is that the nylon stiffens up the tooth. So when you're at high accelerations, your entire transmission system for your XY motion system relies on the pulley to belt interface. And that pulley to belt interface, if you have a high, again, this is the pulley, this is the belt, and if we apply a high load, we're going to see some deflection there. But the nylon facing stiffens up the teeth, and go there and run your fingers over the teeth, and so you're going to get much less deflection and a higher settling load. So the teeth seat much more accurately, and they have less kind of deflection under load. So yeah, EPDM is the kind of backing material which forms the main structure by volume of the belt, but then the facing is nylon, which is what's making it slightly brown. And then the cordage in the belt that runs along the length, which is what gives it its stiffness, is aramid fiber. These belts are made by Gates, which are the original developer and maker of the whole GT2 pulley standard, and they use a lot more aramid in their belts than the kind of cheap knockoffs, because the aramid's the expensive part. It's what makes up the majority lion's share of the cost in materials of what goes into making a GT2 belt. And so obviously if you want to cut price, it makes sense to reduce the amount of aramid, but the aramid is what provides the stiffness of the belt. Yeah, we have time to go into this. So the other thing is that different aramids have different what we call loss coefficients, which is the efficiency at which a material, like say it's a coefficient of restitution, or the inverse of that is the loss coefficient. Whatever. Basically, you go around a corner and you round a corner, so you have a path like this, and you move in X or whatever, you move in Y. You go think, and then what happens? You go boom, 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 like this, and you see this. People call it like ghosting or ringing, and you see it on your prints when you go around corners. So that's a sinusoidal motion. So it's like simple harmonic motion, as we call it. So it goes boom, 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 boom. So there are two things at play there. One is the amplitude of the that initial curve that you pull out, and that depends on the stiffness of the belt, as we just talked about. So if you put more aramid in there, you end up with a lower deflection because your belt is stiffer. If you put less in, higher deflection. The other one is the settling time. So the relationship, the amount of time it takes for the position to settle. So if you have a very low loss coefficient, you'll get boom like this. If you have a very high loss coefficient, you go boom like that. And that's what you're after. You want very high stiffness with a very high coefficient of loss for a positional belt system. and different types of aramid and cordage fiber have very different loss coefficients. So these really help on the ringing side.
What about the frequency?
Frequency depends on your tension and your mass, and it's independent of the stiffness, I think. Yes. Yeah, it's independent. So the frequency will be defined by the tension. So yeah, everything's planar, everything's extremely stiff and stood off of the single reference plane, which is that plate. We do resolve a very small moment, but that's the pulley. So normally on a H-spot, you have this horrible racking moment that tries to like rip your y-axis kind of apart in two different directions. We still have a moment, but we've just reduced the length of the moment arm to the separation distance between these two belts. So it's very small and it's at the head and it causes basically no rotational deflection. Next. I'm always going to check the time. I have a bad reputation for going over time on these things. I wanted to talk a bit about, because this whole tool changing thing has been a long time in development, and we tried a lot of different methods. And people are always like, why didn't you do this? Why didn't you do that? So things we did try, magnets of all kinds. So obviously electromagnet was the first thing that came to mind. Electromagnets, they take up a fair bit of space. They also consume a lot of current and get quite warm. And they're hard to sneak into a small tool head without causing issues. And you generate quite a lot of heat and you dissipate all of that heat. And so electromagnets were quite quickly thrown out of the loop because of the amount of holding force for the amount of heat generated was just basically unmanageable without increasing the size of the electromagnet too far. So there is another thing that is less well known called an electropermanent magnet, which is basically like a permanent magnet that you can turn on and off. So you'll know in a permanent magnet you have all these domains, they call them, and each one has a kind of magnetism. And in a normal, like non-magnetized object, all of the domain fields are all over the place and they will basically cancel out and average to zero. And then if you align or magnetize an object, you align all of its domain fields. So you can create a magnet basically that you can electronically scramble the domains, and then when power isn't applied, it won't be a magnet. And then when you unscramble them and magnetize it and point all the domains in one direction, which only requires a momentary pulse of power, you can actually turn off the tool head, and not turn off the tool head, turn off the power to the kind of the whole device, and it will remain a permanent magnet despite having no power. So we tried those. They're just really big. They're also extremely expensive, so they're like 50, 60 euros a go, and they're quite hard to procure. So we wrote those off. My personal favorite that I really liked, but we ditched, was the vacuum coupler. So if you ever see in automotive factories and they're picking up these body panels, those, and you see these like the frames with like suckers on the end. So you have a vacuum pump, and it's kind of like the Bowden system of grabbers, because you're moving all the electromechanical mass and taking it off the tool head, and then all you have to run is a tube up to the tool head, and you have a very lightweight gasket up there that you just suck onto. We didn't do that because the pumps are expensive and they're also very loud, or like choose any two. Like you can have it cheap and loud, or you can have it like expensive and quiet. Yeah. So we also had concerns about reliability. And just talk about reliability. Bear in mind that you, in a single print, will probably have over 1,000 changes of the print head. And that's in a moderate print. If you have 300 layers in a print, which is pretty normal, then you've got, and you print 4 different materials on each layer, you've got 4 times 300 toolhead changes. You've got a lot of toolhead changes. So even if you have a thing that is reliable 99.99% of the time, it will still probably fail on every print. So it has to be extremely reliable, and the price of failing is quite high, because then the tool head falls off and it's in the print and everything's smashing into everything else. It's really not great at all. So yeah, it's a very punitive system if things go bad in terms of reliability. And we were concerned about kind of print crap, or like strings or otherwise getting in and breaking the seal with the gasket. And there are also concerns about how settling with the kinematic couplings, which I'll go into in a moment, would work. In my opinion, that worked quite well. But yeah, we ended up not going with the vacuum sucker because it was kind of expensive and loud, or expensive or loud. Pick your poison. So what we did, and clicky clacky latching mechanisms, lots of people are like, oh, why didn't you just have like I don't know, a slot that you put it into and then you pull it off like that? Or you can have like a toggle mechanism that's kind of like a ballpoint pen, but it comes apart, so you like clunk and grab it and pull it off. So for the bistable, like clicky pen thing, they tend to be quite large and a little bit unwieldy, and can also interfere with the kinematic couplings, which you really don't want to interfere with, which I'll get into in a moment. The other one is the going in and having like a sideways motion to plunk the head on and a sideways motion to take it off. And we didn't go with those because it means that you need more space for your tool head, and we're already quite space constrained, and unless you have 3 to 4 tool heads at a minimum, it doesn't make any sense to do tool changing, right? You may as well just go IDEX if you can only fit 2 of your tool heads in. So we had a bit of space constraint, so we want to pack as many tools in so you get more fun, but yeah, if you have to have a sideways motion and then all the space for a side, print head in the side head, it just takes up a lot of space, traverse space, that could be filled with other tools. So to talk about what we did and why, we're using like an RC aircraft hobby servo. They're very small. They also have like a next to negligible weight. If you use the micro servos, well, I'm not familiar with all the servo nomenclature, but we're talking about the ones that are about yay big, and that's what we need. They're extremely small. They weigh just a few grams. They're easy to drive off of the board. So most firmwares have built-in support for driving a servo. That kind of got baked in when people were doing the servo swinging Z Pro thing. So kind of quite easy to implement. They're very lightweight. They're pretty damn cheap, depending on how much money you want to pay. They don't really have much noise or require any. They don't generate much heat when they're, so that they really can, because they're a true servo system, i.e. they have a feedback position loop. They are not using much current to hold position unless you provide a deflection, or they have to move when there's basically no current going to, so they don't generate much heat. And yeah, like I said, light, small, cheap, plenty of torque, and range of motion in order to activate the coupling system. Kinematic couplings are so the servo does the kind of the grabbing act, but the actual positional accuracy is done by something called a kinematic coupling, which is a very precise type of locating system that was first kind of conceived of and like theorized about by Kelvin and Maxwell way back in the day, and then they were kind of rediscovered by a guy called Alexander Slocum at MIT, who wrote a bunch of really amazing lectures. You can go. He's now retired, but his work, his lectures are still available on a website called PERG, or Purgatory, which is the Precision Engineering Research Group at MIT, and they just work on very precise systems. So if you want to learn more about kinematic couplings, go there. But effectively, so any object has 6 degrees of freedom, and when you want to position something, you want to remove all 6 degrees of freedom. What we have are these V-shaped grooves, and then a ball sits into the V-shaped groove. So, and these are displaced at 120 degree angles around, and then the two plates provide more angles. So each of these, when the ball makes contact with the groove, and to each contact removes 1 degree of freedom, because they're placed in all the angles going around. So no two are at the same angle. So you have 6 points of contact, removes 1 of the degrees of freedom, so you end up constraining all 6 degrees of freedom by maintaining contact of the balls into these V grooves. So there's no over constraint, there's no redundant positions. So it's not like a 4-legged table, it's like a 3-legged table, just with the additional, a 3-legged table on a plane it has rotational stability. So it's removed the 3 rotational, but it's not necessarily locked all of the translational degrees of freedom. So the V-shape coupling system has to do is provide what we call a settling force, which forces the balls into those grooves. So the way that it works is there is a T-shaped bar that goes into that middle slot up there. It goes in and then it rotates 90 degrees. In the process of the T-shaped cam surfaces on it, cam slot, and kind of screw into it, the slot. And so it pulls its drive shaft itself forward, and there's a spring on the drive shaft. So that stiff spring provides a very high degree of settling force on those couplings. This is a gnarly prototype where these are held by hand, but in production, well, basically aluminium is just about the worst metal you can choose for making a kinematic coupling from, because it frets, it's soft, and it has very high friction.
What are you going to use?
So in production, we're going to grind these surfaces and use a hardenable stainless steel. You'll also note that there's a little bit of grease, and that lubrication helps the couplings into their final location very accurately. And so, yeah, in production, it's just like any other bearing surface. We will, you want ground, hardened, high surface finish steel. Everything on the coupling system. Anyone, any questions on how the system couples? All good. Electronics, we use a duet. 2 main reasons. One is that it has enough I/O to drive all 4 heads, the transheaters, read in all the temperatures. Not many boards out there simply just have all the I/O for plugging in all of these things for 4 heads. The other reason, which is really significant, is that the firmware on the thing about everything you can change through. You have layered architecture of G code, and you have G codes called, and so all the slicer has to do is issue a T0 or a T1 or 2 or 3, and then the printer knows to go away and execute the tool change script, which has like conditional G codes in it, i.e., kind of like if statements in your G code. And it goes away, it knows where to pick up the next head, it knows where to drop off the old head, it knows how to do a wipe script. So for example, the tool change script calls the wipe script as a subroutine, and then the print start script also calls the wipe script as a sub. So you can you've got all of this level of scripting that allows you to do these things like remember when to put back the old head and so on and so forth, or that you have to, things like you can't do auto bed calibration with a hot end picked up because we have BL touch, and that's actually located up in the main carriage, not on the hot end, so you need one BL touch. So it knows that you have to put away the head first. Like, all of this intelligence is built in with the scripting language. Away the head first. Like, all of this intelligence is built in with the scripting language which is G code, which is the scripting language. All of that is built in, and it would be a nightmare to have to go and tear apart Marlin in C++, and the code base in Marlin is really non-trivial in terms of its kind of spideriness by this point, with so many contributors. So it's really, really freaking nice. So if you're ever building some sort of custom strange 3D printer, then I really thoroughly recommend going with a Duet, because it's going to allow you to implement those oddities in a really nice scriptable G-code fashion. So it's going to allow you to implement those oddities in a really nice scriptable G-code fashion. So it's really, really good. But like I say, we are supplying the machine. Yes, we'll have a reference implementation. We'll be releasing the firmware with all the scripts on board, open source. We do want to encourage other manufacturers of electronics and all to be able to go and write their own firmware or implement these features as features within their firmware, so that tool changing can kind of just be on more platforms. So whilst for the hobbyist and the maker, the obvious choice is to go with Duet. If you guys want to buy one of these machines and use it yourselves, Duet is the obvious choice. That we're not supplying it because we want to encourage the adoption of others, and so it's separate. Calibration. People always like, calibrating all of these four heads is going to be a total nightmare. So we found a really easy way to do it. We print vernier scales. So vernier scales are on the old school calipers, so the non-digital ones, ones without the dial, where you have the lines that you kind of line up, and you go along. You have to look for the two lines that are most accurately aligned. They rely on your visual acuity, so your ability to absolutely tell distances is very poor. The human brain is a relative machine rather than an absolute machine in terms of what you can resolve visually. So by using the ability for the eye to distinguish between very small misalignments, you can then kind of hijack that with these what we call vernier scales. If you have the human go along and choose which two lines are best aligned, they can do that with a very high degree of reliability and accuracy. They can pick the two lines that are best aligned. But if you ask a human to tell you how much is that gap in microns, then they're not going to be able to do it. So we go along and we print 3 of these tracks. So you start with tool 0 or tool 1, the first of the 4 tools. With tool 0, you print. If this is, you print 3 scales in Y, and then 1, 2, 3 in X with all the notches. Then you come along with tools 1 to 3, which is the 2nd to 4th tools, and you come along and you print your vernier scales next to them. And it's extremely easy. You go along and you look and you find which one is most well lined up and count how many notches away it is from the center. Each notch is a 50 micron count, so you just count which one, how many notches off the middle it is, and you minus that from your offset. We would like to do this automatically, so we're building a print head. This one on the left is a tool that it has a Raspberry Pi Zero, which is a grey circuit board you can see there, and then on the underside there's a the new Raspberry Pi 2 fanciest, latest camera. And that's a 1080p camera. And then we're putting a macro lens on the front of that, so it becomes like a microscope almost. And what we want to do with this, so is trivial. They're all difficult, but as far as vision tasks, it's about as trivial as it gets, because you've got a surface with a perfect background that you can modify and alter. So you've just got the bed surface, and you know what color it is, you know what you expect. You know it's going to be consistent and flat all the way through. And then you have these two very distinct high contrast colors that you're putting onto that. Maybe you have a black surface, and if you're printing white or bright colors, it's going to be super easy. And if you're printing white or bright colors, it's going to be super easy in computer vision to threshold those out and figure out how much they're misaligned by, or just do the linear thing and choose the one that is most well aligned. So yeah, while no computer vision task is trivial, this is about as trivial as it gets. So yeah, while no computer vision task is trivial, this is about as trivial as it gets.
Put an LED on the hot end.
Put
an LED so you can shine light down.
Yeah.
That will help a lot with the vision.
Oh yeah, we're putting, you can see it just poking out here, the gray thing. There's an LED ring, so you can buy off the shelf these rings of LEDs. I don't know what they're for actually, but you can buy them, these little LED illumination, like 100 LEDs, bright white LEDs spaced around. So this camera toolhead has a bunch of uses, so we can put it on, and then a script that we're working on at the moment. So what happens is you go along, after you've printed the layer, you go along, you grab the camera toolhead, and you can divide the bed's a 200 by 300 bed into under portions. And so you can divide the bed into 6 squares of 100 millimeters, and you take a photo 100 square, and then you can stitch them together, which is a fairly simple operation if you know exactly what the spacing was already. And then you have a set of slides where you can exactly what the spacing was already. And then you have a set of slides where you can verify that each layer was printed properly as it was printed. So you can store all of those and have them go back for inspection and kind of quality. Just into the aerospace, medical, defense crowd. We call them the blank check industries. Those guys are, yeah, it makes a lot of sense for those. And it's just a nice feature to have, to be able to verify that things printed properly. And it's also nice for these auto calibration routines. Also, people ask how to get the Z offset, because there is some Z variation. You just peel the thing off the bed and caliper it in the case of with the measure the width, and you check that it's if you're appropriately volumetrically calculated an extrusion width that is as you define in the slicer. If it's too wide or too low, if you're working with actually more than like few companies have said that next machine. And so E3D a lot. That's damn it. But so yeah, the whole deal is that we really want other people to be able to enter their marking. So defining it sounds really important. We want to put lasers on there because it's a really easy task to do. But more realistically, we can use it for part marking and etching. I want to experiment with using it. We can use it for part marking and etching, and I want to experiment with using it for subtractive manufacturing, for hybrid manufacturing, for trimming, because if you can do that with a laser, that would be great. You print a layer and then trim it to size with laser cutting, and because you've only got a very almost paper thin slice of plastic to trim off, then that should be possible with a diode laser rather than a CO2 laser, or even more than that. So it should be quite cheap and easy. If that doesn't work, we'll have to go with the old spinning sharp thing routine, which is, you know, as a species, we've got a lot of experience with doing that. It just means that there's going to be tool forces and things like that. But we're quite set on, regardless of how well the laser thing works, we're quite set on having a spinning tool head for machining. We've got quite a lot of experience, and it's the task that we're asking this effectively milling machine to do is a very, very lightweight milling task. Because like I said, we have a paper thin piece of plastic to trim off of the edges. So we're going to be able to get away with a very low power motor. We're still going to need very high RPMs because small milling cutters require very high RPMs, and plastics in general, you want a high RPM. So we're going to have a small, well-balanced motor that doesn't vibrate a lot. So we're going to have, it's going to be, you know, there'll probably be a fairly high-end BLDC, small motor, because these high RPMs mean that if you don't have everything really well balanced and it's not a very high quality system, then it's going to vibrate and that's going to cause a lot of issues. So we're designing the tool head already. We have some kind of placeholder CAD for that. Inkjet, yes, you can do the pretty color thing like XYZ, do the full color printing where they come in jets and things, but that's not really interesting to me. Full color printing, I think, especially in FDM, is a bit of a, I don't know, it doesn't make much sense to me. But what we can use the inkjet for is jet release agent onto the top of support material. So you can, and there are various release agents that I think will work well with this. But basically you print your support material, and then in the same material is whatever you want to print, and then you fire some kind of agent onto the top that allows the plastic to stick to it and be supported but break away cleanly at the end. And then pick and place is something I'm really excited about, because pick and place will allow you to insert components mid-build. So imagine a situation where you have a wheel and you want to have a bearing in the middle of that wheel. And so we could have a wheel where we have a flexible specific head to print the tire around the outside. We have a carbon fiber reinforced nylon rim. We've got a soluble support material underneath to support that geometry. And we want to place a bearing in the middle. What have a pick and place head? The one I want to try first is, anyone seen those robotic grippers where it's a balloon full of coffee grounds or some other granular material attached? It's on the end of like a stick, basically, or a tube, and you attach it to a vacuum pump. And when you come along over to a component and you kind of squish the floppy balloon full of granular material over the component, and then you turn on the vacuum pump, and it immediately squishes into a very hard, like the granular material packs very densely into quite a rigid, sucks onto contracts and grabs onto the object. And so we should be able to so we're not talking about pick and place, contracts and grabs onto the object. And so we should be able to so we're not talking about pick and placing tiny little SMD surface mount resistors. We're talking about placing fairly macro human scale objects like you would with your fingers on and into parts. And that's me done. I'm out.
Sorry.
That was the end, I promise.
I hope I didn't interrupt too much.
No,
It's okay.
Yeah, no, we're good with that.